Okay, let's get started again. So before I proceed to Bayesian networks, I'm going to talk about a few announcements. So as you probably know, CAR is due tomorrow. P-Progress is due Thursday. And then finally, the kind of the big one is the exam, which is next Tuesday. So everyone, if you're in the room or if you're watching from home, please remember to go to the exam. The exam will cover all the material from the beginning of the class up until and including today's lecture. So all Bayesian networks, no logic. Doesn't mean you shouldn't use logic on the exam. Reviews are going to be in section this Thursday and Saturday. So you get not one, but two review sessions. The first one will talk about reflex and state-based models, and the second one will talk about variable-based models. At this point, all the alternative exams have been scheduled. If you can't make the exam for some reason, then really please come talk to us right now. And just a final note is that the exam is, the problems are a little bit different than the homework problems. They require more kind of problem solving, and the best way to prepare for the exam is to really go through the old exams and get a sense for what kind of problems and questions you're going to be asked. Question? Where is the Saturday session? Does anyone know?
We don't know yet.
We don't know yet. It will be posted on Piazza. Any other questions about anything? I know this is a lot of stuff, but this is probably going to be the busiest week. And then you get Thanksgiving break, so that'll be great. Okay, so let's jump in. So 2 lectures ago, we started introducing Bayesian networks. So Bayesian networks is a modeling paradigm where you define a set of variables which capture the state of the world, and you specify dependencies depicted as directed edges between these variables. And given the graph structure, then you proceed to define distribution. So first you define a local conditional distribution for every variable given the parents. So for example, h given c and a, and I given a. And then you slam all of these local conditional distributions, aka factors, together, and defines a glorious joint distribution over all of the random variables. Okay? And you should think about the joint distribution as the source of all truth. It is like a probabilistic database, a guru or oracle that can be used to answer queries. So in the last lecture, we talked about algorithms for doing probabilistic inference, where you're given a Bayesian network, which defines this glorious joint distribution, and you're asked a number of questions. And questions look like this. Condition on some evidence, which is a subset of the variables that you have observed, what is the distribution over some other subset of the variables which you didn't observe? Then we looked at a number of different algorithms in the last lecture. There's the forward-backward algorithm, which was useful for doing filtering and smoothing queries in HMMs. This was an exact algorithm. Then we looked at particle filtering, which happens to be useful in the case where your state space, the number of values that a variable can take on, it can be very large. And this is an approximate, but in practice, it tends to be a good approximation. And then finally, particle filtering, and Gibbs sampling, which is this much more general framework for doing probabilistic inference in arbitrary factor graphs. And this was, again, approximate. Okay? So far, we've bit off 2 pieces of this modeling inference learning triangle. We've talked about models. We've talked about inference algorithms. And finally, today, we're going to talk about learning. And so the question in learning, as we've seen repeatedly throughout this course, is where did all the parameters come from? So far, we have assumed that someone just hands you these local conditional distributions, which have numbers filled out. But in the real world, where do you get these? And we're going to consider a setting where all of these parameters are unknown, and we have to figure out what they are from data. Okay, so the roadmap, we're going to first start with supervised learning, which is going to be the kind of the easiest case, and then we're going to move to unsupervised learning, where some of the variables are going to be unobserved. Okay, so any questions before we dive in? Okay, let's do it. So the problem of learning is as follows. we're given training data, and we want to turn this into parameters. Okay, so for the specific instance of Bayesian networks, training data looks like an example is an assignment to all the variables. Okay, this will become clear in an example. And the parameters are all those local conditional probabilities that we now assume we don't know. Okay, so here's a question. Which is more computationally more expensive for Bayesian networks? Is it probabilistic inference given the parameters or learning the parameters given data? So how many of you, just use your intuition, how many of you think it's the former? Probabilistic inference is more expensive. Okay, one maybe. How many of you think learning is more expensive? Yeah, that's probably what you would think, right? Because learning seems like there's just more unknowns, and it can't, how can it possibly be easier? It turns out that it's actually the opposite. Yeah, so good job there. And this will hopefully be a relief to many of you because I know probabilistic inference gets a little bit quite intense sometimes, and learning will actually be maybe not quite a walk in the park, but it will be a brisk stroll in the park. And then when we come back to unsupervised learning, it's going to get hard again. So at least in the fully supervised setting, it should be easy and intuitive. So what I'm going to do now is going to build up to the general algorithm by a series of examples of increasingly complex Bayesian networks. So here's the world's simplest Bayesian network. It has one variable in it. Let's assume that variable represents the rating of a movie. So it takes on values 1 through 5. And to specify the local conditional distribution, you just have to specify the probability of 1, the probability of 2, the probability of 3, probability of 4, and probability of 5. Okay, so these 5 numbers represents the parameters of the Bayesian network. Okay, by fiddling these, I can get different distributions. Okay, so suppose someone hands you this training data. So it's fully observed, which means I observe. One time I observed the value of R to be 1. The second day I observed the value to be 3. Third day I observe it to be 4, and so on. Okay, so this is your training data. Okay, so now the question is, how do you go from the training data here to the parameters? Okay, any ideas? Just use your gut. What does your gut say?
Count the number of instances in training data and then divide by 2.
Yeah, count and then divide or normalize. Okay, so this seems a very natural intuition. Later I'll justify why this is a sensible thing to do. But for now, let's just use your gut and see how far we can get. Okay, so the intuition is that the probability of some value of R should be proportional to the number of times it occurs in the training data. So in this particular example, I look at all the possible values of R, 1 through 5, and I just see 1 shows up once, 2 shows up 0 times, 4 shows up 5 times, and so on. So these are the counts of the particular values of R, and then I simply normalize. Okay, so normalization means adding the counts together, which gives you 10, and dividing by 10, which gives you actual probabilities. Okay? It's pretty easy, huh? Yeah, good. Okay, so let's go to 2 variables. So now you improve your model of ratings, so now you take into account the genre. So the genre is a variable G, which can take on 2 values, drama or comedy, and the rating is the same variable as before. And now let's draw the simple Bayesian network, which has 2 variables, and the local conditional distributions are P of G and P of R given G. Okay, so again, I'm going to give you some training data, which each training example specifies a full assignment to all the variables. So in this case, it's D4, and this one it's D4 again, this one's C1, and so on. And the parameters here are the local conditional distributions, which is P of G and P of R given G. Okay? Okay, so let's proceed to do this. And here, following our nose again, we're going to estimate each local conditional distribution separately. Okay, so this may not be obvious why doing it separately is the right thing to do, but trust me, it is the right thing to do, and it certainly is the easy thing to do. So let's just do that for now. Okay, so again, if we look at P of G. So we have to look at only this data restricted to G. And we see that D shows up 3 times, C shows up twice. So I get these counts, and I normalize. And that's my estimate of the probability of G. Okay? And now let's look at the conditional distribution R given G. Again, I'm going to count up the number of times that these variables G and R show up. So D4 shows up twice, D5 shows up once, and so on. Count and normalize. Question?
So if instead of R given G, you had G given R, and then probability R of R, would that cause any differences in the results, like if the order were to be?
Yeah, it's a good question. So the question is, what happens if we define our model in the opposite direction where we have P of R and P of G given R? So then you would be estimating different probabilities. You would be estimating P of R, which contains 1 through 5, and then P of G given R, which would be a different table. So the question is, if you do inference, do you get the same results? In this case, you will get the same results. In general, you're not. Depending on the model you define, you're actually going to get a different distribution, which will lead to different inference results. Yeah. This happens when you have 2 variables and you couple them together and you do things like this way. You're effectively estimating from the space of all joint distributions G and R. But if you have conditional independence and you have, for example, HMM, the order, how you write the model definitely affects what inference is going to return. Okay? All right, so far so good. So now let's add another variable. Okay, so now we have a variable A, which represents whether a movie won an award or not. We're going to draw this Bayesian network. And the joint distribution is P of G, P of A, P of R given A and G. Okay? So this type of structure is called a V structure for obvious reasons. And this, remember, was the thing that was tricky. This was the thing that leads to explaining away and all sorts of tricky things in Bayesian networks. It turns out that when you're doing learning in them, it's actually all the trickery goes away. Okay? So let's just do the same thing as before. So we get this data. Each data point, full assignment to all the variables. So this is D03, corresponds to G equals D, A equals 0, and R equals 3. And the parameters are all the local conditional distributions. And now I'm going to count and normalize. So this part was the same as before. Count the genres. D shows up 3 times. C shows up twice. Normalize. A is treated very much the same way. So 3 movies have won no awards. 2 movies have won 1 award. So the probability of a movie winning an award is 2 out of 5. And then finally, this is the local conditional distribution of R given G and A. And here we have to specify for all combinations of all the variables mentioned in that local conditional distribution. I'm going to count the number of times that configuration shows up. So D01 shows up once, right here. D03 shows up once, right here, and so on. Okay? And now when you normalize, you just have to be careful that you're normalizing only over the variable that the local distribution is on, in this case R. So for every possible unique setting of G and A, I have a different distribution. Okay? So D0, that's a distribution over 1 and 3, and if I normalize, I get half and half. And each of these other ones are completely separate because they have different values of G and A. Okay, any questions? All good? All right, so that wasn't too bad. So now let's invert the V and look at this structure where now we have genre. There's no award variable, but instead we have 2 people rating a movie. And the Bayesian network looks like this, the genre, and we have R1 given G, and R2 given G. And for now, I'm going to assume that these are different local conditional distributions. So we'll have P R1 and P of R2. So notice that in this lecture, I'm being very explicit about the local conditional distribution. Here, instead of just writing P of G, which can be ambiguous, I'm writing P of G to refer to the fact that this is the local conditional distribution for a variable G. This one's the one for R1, this one for R2, and those are different. And you'll see later why this matters. Okay, so for now, we're going to go through the same motions. Hopefully, this should be fairly intuitive by now. You simply count, normalize for the P of G. And then for R1, I'm just going to look at the first or the second element here, which corresponds to R1, and ignore R2, right? So G R1, so D4 shows up twice. So I have D4 and D4, that shows up twice. D5 shows up once, that's a D5. C1 shows up once, and C5 shows up once. Okay, and then normalize, get my distribution. And then same for R2. Now ignoring R1, I'm going to look at how many times did G equals D and R2 equals 3. Okay, so you can think about each of these as a kind of a pattern that you sweep over the training set. So you have D5, so that's a 1 here, and D4, that's a 1 here, and D3, that's a 1 here, and so on and so forth. Okay, and then you normalize. Okay? How many of you are following this? Okay, cool. All right, so now things, I'm going to make things a little bit more interesting. So here I've defined different local conditional distributions for each rating variable, R1 and R2, right? But in general, maybe I have R3 and R4 and R5, and I have maybe 1,000 people who are rating this movie. I don't really want to have a separate distribution for each person. So in this model, I'm going to define a single distribution over rating condition on genre called PR. And this is where subscripting with the actual identity of the local conditional distribution becomes useful. And this allows us to distinguish PR from this case, which is PR1 and PR2. Okay? Notice that the structure of the graph remains the same. So you can't tell from just looking at the Bayesian network. You have to look carefully at the parameterization. Okay, so if I just have one PR, what I'm going to do is, what do you think the right thing to do is if you were just following your nose? I'm sorry? Yeah, so count both of them, I think is what you're saying. So you combine them, right? So P of G is the same. And now I only have one distribution I need to estimate here, R given G. And I'm going to count the number of times in the data where I'm using, I have a particular value of G and a particular value of R. Okay, and I'm going to look at both R1 and R2 now. Okay, so D3 shows up once here, so that's R2. D4 shows up 3 times, so once here with R1, once here with R1, and once here with R2, and so on. I'm not going to go through all the details. And then you count and normalize. Another way you can see this is that if I take the counts from these two tables, I'm just kind of merging them, adding them together, and then normalizing. Question?
The R's are IID, like that they're drawn from the same distribution, or?
Yeah, so is this assuming something about independence here? So here, when I am assuming the data points are independent, first of all. And moreover, I'm also assuming the conditional independence structure of the Bayesian network is true. So conditioned on G, R1 and R2 are independent. Yeah, so here I'm also assuming that R1 given G has the same distribution as R2 given G. And this is part of the, when I define the model that way, I'm making that assumption. Okay, so this is a general idea which I want to call out, which is called parameter sharing. And parameter sharing is when the local conditional distribution of different variables use the same parameters. So the way to think about parameter sharing is in terms of powering. So you have this Bayesian network, it's hanging out here, and behind the scenes, the parameters are kind of driving it, right? And you can think about the parameters as these little tables sitting out there. And you connect a table up to a variable if you say this table is going to power this node. Okay, so what parameter sharing in this particular example is saying this distribution of G powers this node, and these two variables, R1 and R2, are going to be powered by the same local conditional distribution. Okay? So, okay, I'm going to go to two more examples. Maybe I'll draw them on the board to make this a little bit more clear. So remember the naive Bayes model from 2 lectures ago. So this is a model that has a variable that represents, adapted to our movie genre setting. We have a genre variable, which takes on values, comedy and drama. And then I have a movie review, which represents a document with L words in it. And each word is drawn independently given y. So I have, and the joint probability is therefore going to be probability of genre y times the probability of wj given y for all words j from 1 to L. Okay? So the way to think about this graph, the Bayesian networks, is you have a variable y here. And so I'm just going to draw W1, W2, W3. And I'm going to have a local conditional distribution here, which is y, p genre of y. So that's some table that's powering this node. And then I have a separate one single other of variable, local conditional distribution of y and w, and probability of what do I call it? Word w given y. And this distribution powers these variables. Okay? So notice that here there's two local conditional distributions. We have genre and we have word, even though there are L+1 variables in the Bayesian network. Yeah?
So local conditional distribution is the word. The input for that distribution would be any one of the L words.
Yeah, so the input, so the question is, what is the input to p word w given y? So when you apply this to a particular variable, in some sense you bind y to y, and you bind w to the particular wi at hand.
W1 to WL.
Yeah, exactly. And you can see this kind of mathematically where here we have, you pass into the p word wj given y, and j ranges from 1 to L. Okay. Just to kind of solidify understanding, let me ask the following question. If y can take on 2 values, as in here, and each word can take on d values, how many parameters are there? In other words, how many numbers are in these 2 tables on the board? So shout out the answer. 2D plus 2, right? Mm-hmm. Okay, good. So 2D plus 2, so there's 2 here, right? So there's CD, so there's 2 numbers. And then for every C, there's D possible values. For D, there's D possible values. So there's 2 plus, so there's 2 here, and then there's D plus D here. Okay? Now, if you really want to be fancy and count the number of parameters you really need, it should be less than this, because if I specify the probability of C, then you can 1 minus that probability is probability of D, but let's not worry about that. Okay, let's do the same thing for HMMs, just to make sure we're on the same page here, since we all love HMMs. Okay, so in HMM, remember there's a sequence of hidden variables, H1, H2, H3. And for each hidden variable, we have E1, E2, and E3, which are the observed variables. And there are 3 types of distributions for HMMs. There is the probability of I'm going to call P start of H, which is going to specify the initial distribution over H1. I'm going to have the transition probabilities, which I'm going to denote H, it's called H prime, probability of H prime. Oh, I should write down P trans here. H prime given H. So this is going to be another distribution, which powers each transition, each non-initial hidden variable. Okay. Remember, these are pointing to variables, not edges or anything else. And finally, I'm going to have a distribution, the emission distribution of E given H. That table is going to power each of the observed variables E. Okay? And here, again, there are 3 types of distributions: start, transition, and emission, even though there could be any number of variables in actual Bayesian network. Okay? And just to be very clear about this, when I apply this table to this node, H binds to H1, and H prime binds to H2. And then when I apply it to this node, H2 binds to H, and H prime binds to H3. And again, you can see this from the formulas where I'm passing in to P trans Hi given Hi minus 1 as I sweeps from 2 to n. Okay, so you can think about this as like a little function with local variables. The argument to that, that function are H and H prime. But when I actually called this function, so to speak, when defining the joint distribution, I'm passing in the actual variables of the Bayesian network. Okay, any questions about this? Okay, maybe to summarize some concepts first. Okay, so we talked about learning as generically the problem of how we go from data to parameters. And data in this case is full assignments to all the random variables. In the HMM case, it's a data point is an assignment to all the hidden variables and the observed variables. And parameters, usually denoted theta, is all the local conditional distributions, which are these 3 tables in the case of HMM. Okay. The key intuition is count and normalize. which is intuitive, and later I'll justify why this is an appropriate way to do parameter estimation. And then finally, parameter sharing is this idea which allows you to define huge Bayesian networks, but not have to blow up the number of parameters because you can share the parameters between the different variables. Okay, so now let's talk about the general case. So hopefully you kind of understand the basic intuition. So this is just going to be some abstract notation that's going to kind of sum it up. So in a general Bayesian network, we have variables x1 through xn, and we're going to say that parameters are a collection of distributions. So theta equals p sub d, okay? And so big D is going to be the set of types of distributions. So in the HMM case, it's going to be 3 types: start, trans, and emit. So basically, that's the number of these little boxes that I have on the board there. And the joint distribution, when you define a Bayesian network, is going to be the product of P of xi given x parents of I. So this is the same as we had before. But now notice the crucial difference, which I've outlined in red here, is that I'm subscripting this P with a di. Okay? So what di for the ith variable says is which of these distributions is powering that variable. Okay? So d of this variable is emit, d of this variable is transition, and d of this variable is start. Okay? So this looks maybe a little bit abstract and notationally, but the idea is just to multiply in the probability that was used to generate that variable or power that variable. Okay, and parameter sharing just means that di could be the same for multiple i's. Yep.
So in the hidden Markov model case, in which the emission probabilities are all the same for all the variables, like, why do we need multiple emission states? Like, wouldn't it be the same as just drawing from the same distribution 3 times?
Yes, so the question is, if we only have one emission distribution, why do we need so many of these replica copies? And the reason is that these variables represent the object's locations at a particular time. So the value of this is going to be different based on what time step you're at. But the mechanism for generating that variable is the same. Just like if I flipped a coin 10 times, I only have one distribution that represents the probability of heads, but I have 10 realizations of that random variable. Another analogy might be helpful is think about these as like a primitive of like functions in your program that you can call, right? This is like a sorting function, and sorting is just used in a whole bunch of different places, but it's kind of the same kind of local function that powers a bunch of different use cases which are specific to the context. Yeah. Okay, so in this general notation, what does learning look like? So the training data is a set of full assignments, and I want to output the parameters. So here's the basic form. It's count and normalize. So in counting, there's just a bunch of for loops. So for each training example, which is x is a full assignment, and I'm going to look at every variable. I'm going to just increment a counter, which of the d-ith distribution of this particular configuration, x parents I and xi. Okay? And then in the normalization step, I'm going to consider all the different types of distributions, and then I'm going to consider all the possible local assignments to the parents, and I'm going to normalize that distribution. Yeah?
Just to clarify, well, the DI refers to the red table that we're looking at, correct?
Yeah, so the DI refers for the ith variable which red table I'm looking at. Okay, so I've given you already a bunch of examples, so hopefully this, the notation might be a little bit abstruse, but hopefully you guys already have the intuition. Any questions? We're moving on. The main point of this slide is just to say that this is actually very general, and I just didn't do it for hidden Markov models and naive Bayesian. It doesn't work for anything else. Okay, so now let me come back to the question of why does count and normalize make sense, right? So count and normalize is just like some made-up procedure. So why is it a reasonable thing to do? And it turns out this is actually based on very firm kind of foundational principles. This idea of maximum likelihood, which is an idea from statistics that says if I see some data and I have a model over that data, I want to tweak the parameters to make the probability of that data as high as possible. Okay. So in symbols, what this looks like is I want to find the parameters theta. So remember, parameters are probabilities in the red tables on the board. And then I'm going to make the product of over all the training examples, the probability of that assignment. So for every possible setting of the parameters, that assigns particular probabilities to my training examples, and I want to make that number as high as possible. Okay. And the point is that the algorithm on the previous slide exactly computes this maximum likelihood parameters in closed form. So which is really nice. If you think about when we talk about machine learning, we define a loss function, and you can't compute anything in closed form except for maybe linear regression, and you have to use stochastic gradient descent to optimize it. Here, it's actually much simpler because of the way that the model is set up. You just count and normalize, and that is actually the optimal answer. So just because you write down a max doesn't always mean you have to use gradient descent, is a lesson here. Okay, so I'm not going to prove this in generality, but I want to give you some intuition why this is true, and hopefully connect the abstract principle with the on-the-ground algorithm of count and normalize. So suppose we have a two-variable Bayesian network with genre and rating. So I have 3 data points here, and I have this maximum likelihood principle, which I'm going to follow. And let's do some algebra here. So I'm going to expand the joint distribution. And remember, joint distribution is just the product of all the local conditional distributions. And I've also expanded this, the product over these 3 instances. So I have the probability of D, probability of 4 given D, probability of D here, probability of 5 given D, probability of C, and probability of 5 given C. Okay? And what I'm maximizing over here right now is a distribution over a genre, and I have a distribution of a rating condition on a genre as C, and the distribution of rating condition genre equals D. Okay, so I've color-coded these in a certain way to emphasize that all the red touches is the local conditional distribution corresponding to genre. The blue corresponds to probability of rating given genre equals D, and green is probability of rating given genre equals C. Okay, so now I can shuffle things around. Okay, and I notice that these factors don't actually depend on probability of G at all. So they can just hang out over here. And I've essentially, and this likewise, if I'm thinking about the maximum over R given C, these other factors are just constants, so they don't really matter either. So I've basically reduced this as a problem of 3 independent maximization problems. Okay? And this is why I could take each local conditional distribution in turn and do count and normalize on each one separately. Okay, and then the rest is actually, to do it actually properly, you have to use Lagrange multipliers to solve it, but intuitively, hopefully you can either do that or just believe that if I ask you what is the probability, best way to set probabilities so that this quantity is maximized, I'm going to set probability of D equals 2/3 and probability of C equals 1/3. This is similar to one of the questions on the foundations homework, if you remember, but only for probability of a coin flip, essentially. Okay, so hopefully some of you can now rest, sleep at night thinking that if you do counter normalize, you're actually obeying some high-minded principle of maximum likelihood. Okay, so let's talk about a Laplace smoothing. So here's a scenario. If I give you a coin and I said, I don't know what's probability of heads, but you flip it 100 times and 23 times it's heads and 77 times it's tails, what is the maximum likelihood estimate going to be? Yeah, so it's going to be probability of heads is, counter normalize. It's 23 over 100, which is 0.23. Probability of tails is 0.77. Okay, so seems reasonable, right? So what about this? So you flip a coin once and you get heads. What's the probability of heads? So the maximum likelihood says 1 and 0. So some of you are probably thinking, smiling and probably thinking, this is a very closed-minded thing to do, right? Just because you saw 1 heads, it's like, oh, okay, the probability of heads must be 1. Tails is impossible because I never saw it. So it seems pretty, foolish. And intuitively, you feel like, well, tails might happen, sometimes. So it shouldn't be as stark as 1, 0. Okay, and this is an example of overfitting, which we talked about in the machine learning lecture, where maximum likelihood will tend to just maximize the probability. And here it does maximize the probability because the probability of data is now 1, and you can't do better than that. But this is definitely overfitting. So we want a more reasonable estimate. So this is where Laplace smoothing comes in. And again, I'm going to introduce Laplace smoothing from kind of a follow your nose kind of framework, and then I'll talk about why it might be a good idea. Okay, so here's maximum likelihood, just the number of times head occurs over the total number of trials you have. So Laplace smoothing is just adding some numbers. This is Laplace, named after the famous French mathematician who did a lot more than add numbers, like the Laplace transform and Laplace distribution. But we're only going to talk about his adding numbers invention, I guess. So here in red, I've shown that for this probability estimate, no matter what the data is, I'm just going to add a 1 here. I don't care what the data looks like. I'm just going to add a 1, and I'm going to divide by the total number of values which are possible, which is 2, heads or tails. And for tails, I'm also going to add a 1. I don't care what the data says, and I'm going to divide by 2. Okay, so now I get 2/3 and 1/3, which should be a more sensible, intuitively sensible estimate if you're going to come up with any sort of estimate. It says, well, I saw heads, so probably more than 50% it's going to be heads, but it's probably not 100%. Okay, so let's look at it in a slightly more complicated setting. So here I have 2 variables, and Laplace smoothing is driven by a parameter lambda, which by default is going to be 1, but it can be any number, non-negative number. And what Laplace smoothing amounts to is saying, start out with your tables, and instead of filling them up with 0, fill them in with lambda. Okay? So here's my table. Before I even look at the data, I'm just going to put 1s down. And then when I look at my data, I'm just going to add to that counter So D shows up twice, C shows up once, and then count and normalize. Okay, same over here. Before I look at any data, I'm just going to populate with ones, which is lambda. And then I get my 3 data points, and I add the 3 counters, which are shown here, and I count and normalize. So by construction, no event should have probability 0 unless lambda is 0. Because I always start with 1, and 1 divided by some positive number is not 0. Okay? So the general idea is for every distribution and partial assignment, I'm going to add lambda to that count, and then I'm just going to normalize to get the probability estimates. Okay? So the interpretation of Laplace smoothing is you're essentially, pretending that you saw lambda occurrences of every local assignment, even though you didn't see in your data. So you're hallucinating this data. Sometimes it's called pseudo counts or virtual counts. And the more higher lambda is, the more hallucination or more smoothing you're doing. And that will draw the probabilities closer to the uniform distribution. In the other extreme, lambda equals 0 is simply maximum likelihood. But in the end, data wins out. So if you had Laplace smoothing and you saw one head, and now you're saying estimating the probability to 2/3. But suppose you keep on flipping this coin, and it keeps on coming up heads 998 times. Then by doing the same Laplace smoothing, you're going to eventually update your probability to 0.999. You're never going to reach 1 exactly because no probabilities are going to be ever 0 or 1. But increasingly, you're going to be much more confident that this is a very, very rigged coin. Okay? Any questions about Laplace smoothing? So Laplace smoothing is just add lambda to everything, essentially. And so I forgot, the principle behind Laplace smoothing is if you think in terms of, this is kind of beyond the scope of this course, but you can think about a prior distribution over your parameters, which is some uniform distribution. And instead of doing maximum likelihood, you're doing MAP or maximum a priori estimation. So there is another principle, but you don't have to worry about it for this class. Yeah?
How do you know how big to make lambda?
So the question is, how big do you make lambda? It's a good question. So one is, lambda should be small. It probably shouldn't be like 100. Probably should be more like 1, or even, you can make it less than 1. Maybe it should be like 0.01 or something. It depends on how, I guess, uncertain you are. So in general, these priors are meant to capture what you know about the kind of the distribution at hand. Okay. All right. So now we get to the fun part. This is going to, in some sense, combine learning, which we've done, with probabilistic inference, which we did before. And the motivation here is that what happens if you don't observe some of the variables? So far, learning has assumed that we observe complete assignments to all the random variables, but in practice, this is just not true, right? The whole reason people call them hidden Markov models is that you don't actually observe the hidden states. So what happens if we only get the observations? Or in this simpler example, what happens if the data looks like this, where we observe the ratings, but we don't observe the genres? So what can you do? So obviously, the count and normalize thing doesn't work anymore because you can't count with question marks. So there is, again, 2 ways to think about what to do here. the high-minded principle is appeal to maximum likelihood and make it work for unobserved variables. And the other way to think about it, which I'll come to later, is simply guess what the latent variables are and then do count and normalize. Okay? And these two are going to be equivalent. So let's be high-minded for now and think about what maximum marginal likelihood. Okay? So in general, we're going to think about H as the hidden variables and E as the observed variables. In this case, G is hidden and R1 and R2 are observed. And suppose I see some evidence E, so I see R1 equals 1 and R2 equals 2, but I don't see the value of G. And again, the parameters are all the same as before. I just have less data or information to estimate the parameters. Okay, so if you're following maximum likelihood, what does maximum likelihood say? It says tweak the parameters so that the likelihood of your data is as large as possible. So what is the likelihood of the data here? It's simply, instead of H and E, I have probability of E. Okay? So this seems like a kind of a very natural sound extension of maximum likelihood. And it's called maximum marginal likelihood because this quantity is a marginal likelihood, right? It's not the joint likelihood or joint distribution, it's a marginal distribution over only a subset of the variables. Okay, so now to unpack this a bit, what is this marginal distribution? It's actually, by axioms of probability, it's the summation over all possible values of the hidden variables of the joint distribution. So in other words, you can think about maximum marginal likelihood as saying, I want to change the parameters in such a way that the probability of what I see as high as possible, but what that really requires me to do is think about all the possible values that H could take on. I don't see it, so I have to consider what ifs. What if it were C? What if it were D? And so on. Okay? So in other words, fundamentally, if you don't observe a variable, you have to consider possible values of it. Okay. All right, so now let's skip to the other side, the kind of a scrappy way, and think about what is a reasonable algorithm that makes sense. And I'm not going to have time in this course to kind of show the formal connection, but if you take CS221 or a graphical models class, you'll go into this in much more detail. So the intuition here is the same as what we had for k-means. So remember in k-means, you try to do clustering, you don't know the centroids, and you also don't know the assignments. So it's a chicken and egg problem, so you go back and forth between figuring out what the centroids are and figuring out what the assignments are. And the centroids are going to be an analog of parameters here, and the assignments are going to be the analog of the hidden variables. Okay? So here's the algorithm. It's called expectation maximization. It was formalized in its generality in the 70s. And you start out with some parameters, maybe initializing to uniform or uniform plus a little bit of noise. And then we're going to alternate between two steps, the E step and the M step. And it's useful to think about the k-means in your head while you're going through this algorithm. So in the E step, we're going to guess what the hidden variables are, or what the values of the hidden variables take on. So we're going to define this Q of H, which is going to be represent our guess. And since we're in probability land, we're going to consider the distribution over possible values of H. And this guess is going to be given by our current setting of parameters and the evidence that we've observed and are fixing. So we're asking the question, what is the probability of the hidden variables taking on particular values of H given my data and given my parameters? So this should look kind of familiar to you, right? What is this? This is just probabilistic inference, right? Which we've been doing for the last lecture. Which means that you can use any probabilistic inference algorithm here. You can do forward, backward. You can do Gibbs sampling. And that's kind of a submodule that you need to do EM. Okay? Okay, so now what happens if we have our setting of, or guess over the possible values of H? Now we make up data. So we create weighted points with particular values of H and E, and each of them gets some weight Q of H. And then finally, once we're given these weighted points, now we're just going to do count and normalize and do maximum likelihood. Okay, so I'm going to walk through an example to make this a little bit more grounded out. So I'm going to do this on a board because it's going to get a little bit, maybe a little bit hairy. Okay, let's do this. So here we have a 3-variable Bayesian network. So we have, let's draw it over here actually, might need a space. So we have G, we have R1 and R2. Okay, and our data that we see is we get data which is 2, 2 and 1, 2. Okay, so I observe 2, 2, that's one data point, and 1, 2, that's another data point. Okay. So initially what I'm going to do is start with some setting of parameters. Okay? So I'm going to start with my parameters theta, which specify a distribution over G, and for lack of information, I'm going to consider just half and half. Let me write 0.5 to be consistent. So I'm initializing it with a uniform distribution, and my other table here is going to be G and R, so probability of R given G. And here I have C, the possible values of G and the possible values of R, which for simplicity I'm going to assume to just be 1 and 2. And then for this I have, for these numbers, 0.4, 0.6, and 0.6, 0.4. So I'm not setting them to uniform, but adding a little bit of noise. So hopefully people can check that the numbers on the board are the same as the numbers on the slides. Okay, so that's my initial parameter setting. So now in the E step, I'm going to use these parameters and to guess what G is. Okay? So what does this look like? So for each possible data point, so for every example, so I have 2, 2, that's one data point. I'm going to try to guess what the value of G is. So it could be C, it could be D, and for the other data point, 1, 2, it also could be C or it could be D. Okay? And now I'm going to try to compute a weight for each of these data points based on the model. Okay, so the weight is, now look at this. This is cool, right? Because I have a complete assignment. And I know what to do with complete assignments. I can just evaluate the probability of that assignment. Okay, so now just to make things concrete, I have probability of G times probability of R1 given G, probability of R2 given G. This is, by definition, the probability of G 2 equals, sorry, that's a little bit messy, but. So this is joint distribution. By definition of this Bayesian network, it's this. Okay, so how do I compute the probability of this configuration? Well, it's a probability of G equals C. So I look at this table, that gives me a 0.5 times the probability of R1 given G, that's 2 and C. So if you look over here, that's a 0.6. And then another R2 given G, that's also a 2 and a C, so that's 0.6 because of parameter sharing. And that's 0.18, right? Let me advance the slide so you guys can check my work. Okay, so now I look at this table. So the probability of G equals D is 0.5. And then the probability of R1 equals 2 given G equals D. Look in this table, that's 0.4. And then I have another 0.4 from the other two, and that is 0.08. And then I can normalize this. Question?
For T2 versus 0.6 for C2.
So why is this 0.4 versus 0.6 here? This is because I initialize the parameters so that the probability of R equals 2 given G equals D is 0.4.
So I guess I'm wondering, why did you use that initialization?
Why did I use this initialization? Just for fun. I just made it up. Just so that if I had put 0.5s here, then you couldn't really tell what was going on. And also, as a side mark, it wouldn't work. Yeah.
So initialization is always random?
Initialization is generally going to be random, but as close to uniform as possible. Yeah.
Thank you.
Okay, so this column is going to be the probability of basically G equals G, R1 equals R1, R2 equals R2. Okay, and then the Q is going to just be is just going to be the weight of this, and normalizing these two, which means that you add them up and you divide, and then you get, was it 0.69 and 31? Sorry, the numbers are a little bit kind of awkward, but that's what you get there. I'm not going to do the second row, but it's basically the same type of calculation. Question?
Is maximization kind of like particle filtering in that, like, the E step you do like the proposal and then the weighting, and then the M step is like the resampling, like finding the maximum?
So the question is EM expectation maximization is kind of like particle filtering because you have this proposal and you're reweighting. Structurally, it's quite different. I mean, there is a sense like there's some, you're proposing different options, but certainly the two algorithms are meant to solve very different tasks. One is for learning and one is for probabilistic inference. Yeah. Okay, so let's look at the M step now. Okay, so the M step, I'll let you guys fill this in. So the M step, I actually want to keep this up. Let me do the M step over here. Is going to now just take these examples. So these weights are 0.5. So it's like someone handed you fully labeled data, complete observations, 4 points, but each observation has a weight. So now the only difference in count and normalize, instead of just adding 1 whenever you see a particular completeness or configuration, you're going to add the weight. Okay? So for each of the parameters, I'm going to look at, so this is going to be G, probability of G. So this can be either C or D. And to get this, I have, let me first do the count, I guess. Well, okay, let me just add it here. So I look at my data. So let me mark this. So this is now my kind of, I'm going to put data in quotes because I didn't actually observe it. I just hallucinated it. And these are the weights, which are associated with the data points. So now I'm going to look at G equals C. So I see C here, and I have the weights 0.69, 0.69 plus 0.5 probability of, sorry, just count. And then for D, I see a D here and I see a D here. That's 0.31 plus 0.5. And then I normalize this and I get my estimate. Okay, so on the slide, this is exactly what I did here. I count and normalize. And I'm not gonna do this table, but you hopefully get the idea. Yep.
Estimate for all possible assignments of each?
Yeah, so in the each step, you have to estimate for all possible assignments to each. So in this case, h is only one variable. In the next example, h is going to be in a hidden Markov model, all the variables, and we're going to see how we can deal with that. Yeah.
Can you explain briefly how we get the values in the second table?
The second table, which this one? This one.
Yes.
Yeah, sure. Just briefly, so you look at these data points, and you see C1, okay? So where does C1 show up? So G equals C here, R1 equals 1 here, so that's a 0.5 here. And then what about C2? Where does C2 show up? C2 shows up twice here with R1 and R2, so that's why there's 2 of 0.69s here. And C2 shows up once here with a weight of 0.5. Yeah, everything here, these counts are based on the table from the E step. Okay. All right, so let's do something a little bit fun now. So the copial cipher is this 105-page encrypted volume that was discovered and people dated back from the 1730s. So it looks like this. So it's unreadable because it's actually a cipher. It's not meant to be just read. And for decades, people were trying to figure out, what is the actual message that was inside this text. It's a lot of text. And finally, in 2011, some researchers actually cracked this code, and they actually used EM to help do this. So I'm going to give you a kind of a toy version of using EM to do decipherment. And it turns out that this code is basically some book from a secret society, which you can go read about on Wikipedia if you want. So substitution ciphers. A substitution cipher consists of a substitution table, which specifies for every letter, assume we have only 26 right now, a cipher letter. Okay? And the way you apply a substitution table is you take a plain text, which generally is unknown if you're trying to decipher, like let's say hello world, and you look up each letter in the substitution table and you write down the corresponding thing. So H maps to N, so you write N. E maps to M, so you write down an M, and so on. And so someone did this, and then they obviously didn't give you the plain text. They gave you the ciphertext. And so now all you have is a ciphertext, and obviously didn't give you the substitution table either. So all you have is the ciphertext, and you're trying to figure out both the cipher, a substitution table, and also the plain text. Okay? So hopefully this pattern matches something. And let's try to model this as a hidden Markov model. Okay? So here, the hidden variables are going to be the characters in the plain text. This is the actual sequence that the hello world. And then observations are the characters of the ciphertext. So familiar equation, the joint distribution of the hidden Markov model is given by this equation. And we want to estimate the parameters, which include p start, p trans, and p unit. Okay, so how do we go about doing this? So we're going to approach this in a slightly different way, I guess, than simply just running the algorithm, because we have additional structure here, right? So the probability of start, I have no idea. So just set it to uniform. The probability of transition, so this is interesting. So normally if you're doing EM, you don't know the probability of transition. But because we know, let's say we know that the underlying text was English, we can actually estimate the probability of a character given a previous English character from just English text lying around. So this is cool because it allows us to hopefully simplify the problem. I should maybe comment that in general, unsupervised learning is really, really hard. And just because you can write down a bunch of equations doesn't mean that will work. And it's very hard to get it to work. So you want to get as much kind of supervision or information as you can. Okay, so finally, E emit is the substitution table which we're going to derive from EM. Okay, so now this might not type check in your head because a substitution specifies for every letter one other letter, the cipher letter. But in order to fit it into this framework, we're going to think about a distribution over possible cipher letters given a plain text letter. Okay, with the intention that, well, if it's doing its job, it can always put a probability 1 on the actual cipher letter. Okay, so just stepping back away from the formalism, why might you think this could work? And in general, this is not obvious that it should work, but what you have here is a language model, P transition, which tells you kind of what plain text looks like. Right? If you generate a cipher and you say, this is my cipher, and you get some garbage, then it's probably not right. So we have some information about what we're looking for. Like when you solve a puzzle, you know when you kind of solved it. And then finally, we also have this emission that tells us that each letter, that E has to go to kind of be substituted in the same way. So you can't have E going to completely different things at different points in time. Okay, so for doing estimation in HMM, we're going to use the EM algorithm. And remember, in the E step, we're just doing probabilistic inference. And we saw that forward-backward gives us probabilistic inference. In particular, it gives you, for every position, I'm going to give you my guess, which is a distribution over possible hidden variables. So remember, at each position, I observed a cipher letter, and I'm going to guess a distribution over the plain text letter. Okay? And then the M step, I'm just going to count and normalize, as we did before. So once I've guessed the cipher letters, I can just compute the probability of some cipher letter given a plain text letter. Okay? So I'm actually going to code this up and see so you can see it in action. Okay, I only have 5 minutes here, so to make this quick. Okay, so here we have ciphertext. Okay, looks pretty good. We're going to decrypt this or decipher it. And then we also have our text, which is just some English text that we found. And then I'm going to, I want to decipher, not encipher. Okay. So there's some utilities which are going to be useful. So things for reading text, converting things into integers, normalization of weights, and then most importantly, this implementation of a forward-backward algorithm, which we're going to use. Okay, because I'm not going to try to do that in 5 minutes. Okay, so let's initialize the HMM, and then later we're going to run EM on it. Okay, so the HMM parameters are, there's going to be start probability, which is P in our notation, probability of start. And this is going to be 1 over the number of possible letters here. This is just a uniform distribution, 1 over k. And I should say k is 26 plus 1, so this is lowercase letters plus space. Okay, so now we have our transition probabilities. And I'm going to, this is going to define a distribution over hidden variable, next hidden variable given previous hidden variable. And notice that the order is reversed here because I want to first condition on H1, and then this thing is going to be a distribution. So to do this, I'm going to first remember my strategies. I'm going to use the language model data to count. So I'm going to have, again, set things to 0 for H2 in range K, for H1 in range K. So this basically gives me a matrix of K by K matrix of all zeros. And now I'm going to get my raw text, and I'm going to read it from lm.train, which remember looks like this. And I'm going to convert this into a sequence of integers where they're going to be 0 to k minus 1. And then I'm going to, how do I estimate the transition? Again, count and normalize. So I'm going to go through this sequence and I'm going to count every successive transition from one character to another. And I'm going to, so I'm going to, at position I have a character which is raw text of I. At position I plus 1, I have another character, H2, and I'm just going to increment this count. Okay, and finally, I'm going to normalize this distribution. So transition probs equals, so for every H1, I have a transition counts of H1, and I can call the helpful normalize function, which takes this distribution and normalizes it. Okay, so this is just doing fully observed maximum likelihood count normalize on just the plain text. Okay. All right, so now emission probs. This is going to be probability of emit of E given H. And I'm going to just initialize these to uniform because I don't know any better. So 1 over K for E in range K for H in range K. So just so it happens that both the hidden variables and observed variables have the same domain. That's not generally the case. Okay, so now I'm ready to run EM. So I'm going to do 200 iterations just to put in a number. So I have the E step and the M step. So in the E step, remember I'm going to do probabilistic inference. I'm going to call forward backward. And remember this is going to be basically in our notation. At the position I, what is my distribution over hidden states? So this is actually forward, backward. Oh, I need to read some observations in. So I read my ciphertext, and I'm going to convert this again into an integer array. And then I have observations, and then I pass in the parameters of my hidden Markov model. And then I have my guess. So let me print out what that guess is. Okay, so what I'm going to do here is for every position, I'm going to get the most likely outcome of H. So util of argmax of Qi for I in range length of observations. Okay, so that gives me an array of guesses for each position. And then I'm going to convert that into a string so it's easier to look at and put a new line. So this is printing the best guess. Okay, so finally for the M step, I have my Q, which gives me counts. So now I pretend I have a lot of data which are weighted by Q. So I'm going to have emission counts equals same as before. I'm just going to get a matrix of zeros. E in range k for h in range k. And then I'm going to go through the sequence from I equals range of to the length of the observation sequence. And for each position in the sequence, I'm going to consider all the possible plain text hidden values. And I'm going to increment h observations of I. So this is the observation that I actually saw. And this should be QIH, which is the weight of h at position I. Okay? And then finally, I'm just going to normalize. So like what I did, I'll just normalize that here. So emission probabilities is util dot normalize of the counts for h in range k. Okay? And I think that's pretty much it. Let me see if this, okay. This should be 4 E, what? Right? Okay, good. Okay, so let's run this, and then I'll go back to the, let me just go over the code just one more time. Okay, so we initialize the probabilities to uniform. For transition probabilities, we can use the observations or just the plain text. We just count and normalize. In emissions, we initialize with uniform, and then we're running EM. We read the ciphertext, and then in the E step, we're going to use the current parameters to guess where the ciphertext is. And then we're going to update our estimate of what the parameters are given our guess of what the ciphertext is. Okay, so here's the final moment of truth. The ciphertext. And so remember, each iteration, it's going to print out the best guess. So it will look like gibberish for a little bit. It's not going to be perfect. But this starts to look somewhat like English. There's an and in there. Anyone can read this? Alone without. Okay, that looks like English. Maybe this is like anyone that I could. Anyone guess what this text is? So here's the plain text. So I lived my life alone without anyone that I could really talk to until I had an accident with my plane in the desert with my whatever, something. but so again, unsupervised learning it's not magic. It doesn't always work, but here you at least see some signal. And in the actual application, they got partway there, and then you can iterate on this kind of in a manual way. Okay. Oops. All right, so that's it for Bayesian networks. On Wednesday, we'll do logic.